All right, hello everyone. So today's the first day that we're officially going to be learning something new as far as where we left off. So a reminder, where we left off was the fundamental counting principle, which we reviewed in yesterday's lesson. So if you forget that, you can always go back and check that out. This is kind of the agenda for today. We're going to start out just by doing a quick kind of vocab touch in, because we've been seeing a lot of these words like permutation and combination. If you went on Khan Academy, you would have seen that under the practice that we were doing for the fundamental counting principle, they actually labeled it as permutations, which is a word we haven't yet seen. So I want to go ahead and define that at the beginning of class today. And then after we kind of discuss the difference between permutations and combinations, we're officially going to get into talking about probability. So we have done some discussion over like using the word probability, but we actually haven't found anything to do with probability yet. The fundamental counting principle is something you use and then you use as part of finding the probability, but that's not actually the probability of getting something. So when we did the fundamental counting principle, and if I go back to the worksheet from last week and we look at this, the fundamental counting principle basically says how many possible outcomes are there total. Given the pattern that we're looking at, given the restrictions, how many possible outcomes are there? But that doesn't give me the probability of, looking at, rolling the dice. That doesn't give me the probability of rolling a 5. It's simply telling me how many possible ways do I have to follow this pattern. Okay, so we'll start looking at probability. If we have time, we'll talk a little bit about Venn diagrams, which hopefully you've seen before, so that shouldn't come as new. We also want to talk about the and versus the or when it comes to probability. And then finally, we'll touch on mutually exclusive and what that terminology means. Again, hopefully if we have time. So let's start out our discussion with talking about permutations versus combinations. Now, combinations may be a word that you are familiar with, or at least think you're familiar with. So take a second and ask yourself, where have you heard the word combination before? Combination. And if you can think of quickly something that, you've heard someone say, oh, this is a combination, or you think you know the definition of combination, I want you to then think to yourself, what's the definition of a permutation? Have you ever heard of a permutation? Those of you that have done the Khan Academy, have you figured out what the word permutation is? So take a second yourself. Where have you heard the word combination before? Where have you heard the word permutation before? Have you heard the word permutation before? Well, the problem is permutation and combination in today's society are quite frequently mixed up. A lot of times people use the word combination when they should actually be using the word permutation. So really, what's the difference between a permutation and a combination? Well, let's stop and think for a second. Think back to your lockers. Each of you have a locker, or had, I guess, a locker in the school. In which case you had we'll call it a password or a code that would get you into your locker. Let's just say, thinking of some random numbers, 17, 15, 37. Maybe that's your locker password, okay? But here's the thing. A lot of you would refer to this as your locker combination. But this is not a combination. So you may be wondering to yourself, well, I've always called it a combination. Heck, as an adult, looking back on my high school career, I would still refer to this as a combination. And I would say, this is my locker combination. But it's actually not a combination. It's a permutation. So let's look at the difference between a permutation and a combination. The one big key factor between a permutation and a combination is this. Permutation order matters. Versus a combination, order doesn't matter. Which again, thinking back to this code that you would use to get into your locker, we normally would say that this is your locker combination. But it's actually not a combination, which is the crazy thing about this. Because if you think about it, if you go up to your locker, and let's say this is the code that gets you into your locker. If you go up to your locker and you attempt to do 37, then 17, then 15, will that get you into your locker? No, because this is the code that you need to get into your locker. Not 37, 17, 15. Even though they're the same numbers, they have a different order, making them a different code. And therefore, if you try this combination, or even if I tried 17, 37, and 15, it's still not going to work. Because with a locker code, order matters. So that's what makes it a permutation and not a combination. So it's a really hard habit to kick, saying, oh, this is my locker combination. It's not a locker combination. It's a locker permutation, okay? And that's where society has gotten it wrong. And they always call it a combination, and a lot of teachers say, here's your locker combination. That's wrong. They should be calling it a permutation. Permutation is where order matters. So, if locker permutations are an example of permutations, not combination, then what's an example of a combination? Good question. So, an example of a combination would be this. Let's say that, I'm standing here. Here's Miss Maurer. Whee! Okay? And she gets to take 5 people on a field trip. So I get to pick 5 people to come on a field trip with me. Well, let's say that I pick Timmy. I'm going to pick Rob. I'll pick Rose. I'll pick Katie. And I'll pick Donna. Okay, those are the 5 people that I have picked to come on this field trip with me. Okay? Now, if I went through and I said, well, what if I decided to pick, Rose, then Rob, then Tim, then Katie, then Donna? Does it matter that I picked Rose first? No, because they're all getting to go on the field trip. So it's still the same 5 people, and changing where I wrote Rose and Tim is not going to change who gets to go on the field trip. Versus down here with the locker permutation, changing the order of these numbers makes the combination not work anymore. So down here, the order matters. But over here, with picking who's going to come on the field trip, it doesn't matter who I picked first and who I picked last. These 5 people are still going to get to go on the field trip with me. So if I try to figure out how many combinations of people I could take on the field trip, I wouldn't have to include all the different ways that I could write this with, Tim, then Rob, then Rose, then Katie, then Donna, or Rose, then Rob, then Tim. This would all still just be one outcome. Okay, regardless of the way that I write them, the order does not matter. This would be one outcome. Versus down here with the numbers 17, 50, and 37, there are multiple ways that I can write this code, but only one of them will actually work. Therefore, the order in which I write the numbers do matter. So that's the big difference, is you have to know the difference between a permutation and a combination, because again, combination is a word that people misuse all the time. Okay, so again, locker permutations. If you say that to a math teacher, they'll get so excited because they'll be like, oh my gosh, you know what a permutation is. Okay, so that's the first kind of big thing that I wanted to hound in, because if you were doing your Khan Academy like you should have been doing last week, you would have come across that word, and I wanted to make sure we were all aware of what the word permutation means. Now, we will be focusing primarily on permutations over combinations, but I wanted you to be aware of the difference of those, because a lot of times people see combination and they think they know what it means, but they actually don't. Okay, combination order does not matter. Permutations order does matter. So when you're thinking of all these word problems from last week, you can even go back and look through them. Does the order matter? Does it matter if I come in and look at an example? Does it matter when I'm rolling the dice whether I roll the red one or blue one first? Yes, because the red dice is going to represent one number and the blue dice is going to represent something else. Coming down to number 5, again, you can, go on number 5 and look at it. Let me see if I can get you to see number 5 a little bit clearer. But if you look at number 5, it says, from a standard deck of cards, how many ways can you pick a king, a hearts, then a 5? They're telling you a specific order. They want the king drawn first, the heart drawn second, and the 5s drawn third. If they asked you how many ways can you pick a hearts, then, 4s, then something else, that changes the game. Now, you will notice in that particular example, the numbers aren't going to change much, but there are many situations in which, especially dealing with passwords to computers and things like that, the order does matter. Like I said with the locker permutation, not combination. Okay, locker permutation. So we're on to the next part, and the exciting part, in my opinion, is finally talking about probability. So the question arises, well, what's the difference between probability and the permutation and combinations that we are talking about on the front? Permutations and combinations basically simply say how many possible outcomes are there. If I wanted to, make a new password for my computer using 3 letters and 2 digits, how many possible passwords can I create? Okay? But probability is saying, what are the odds that I get a specific outcome given all the possible outcomes that I have? So let's just take a very, very small example and consider a dice for a second. Okay? So I have a 6-sided dice, right? So on a dice, there are 6 possible outcomes. I could get a 1, a 2, a 3, a 4, so forth, and so on, right? But then, if I said, what are the odds, or what is the probability of me selecting a 2? Very specifically, a 2. What is the probability that I select a 2? Now, the key here is probabilities are always in percent form. Okay? When I ask for what's the probability of selecting a 2, I want to know what's the percent. What are my chances of picking a 2? So, to set up a probability, it's very, very simple. You're basically going to take the amount of outcomes. So out of rolling a dice that has 6 sides, I want to know what are the odds that I'm going to pick specifically a 2. So how many times does 2 appear on a dice? It only appears once out of the 6 sides that I have. So the probability of selecting a 2 is 1 out of 6 options. So out of all the pieces on a dice, only one of those sides is a 2, and therefore only one of my 6 outcomes will give me what I want, which is a 2. Okay? So if I go ahead and calculate that, and again, keep in mind 1 divided by 6, 1 divided by 6, that gives me approximately, I'm going to round a little bit, 0.17. Now that is a decimal, right? So how do we convert a decimal to a percentage? How do we convert a decimal to a percentage? How do we convert this decimal to a percentage? Well, hopefully quickly you say multiply it by 100. So if I multiply this by 100, that should give me my percent of about, we'll again round, 16.7%. So if I was a gambling person and I said, oh, I'm going to bet $100 right now, right here. I'm going to bet with my whole class. I'm going to bet $100 saying that I can roll a 2. And then I take my dice, and then I roll my dice. If I don't get a 2, I lose my $100. If I get a 2, then, whatever the betting was, I would win, right? But here's the thing. The odds of getting a 2 is only 16%. Well, you could round it up to 17 if you feel like being confident, but it's only 17%. So the odds of getting a 2 and winning the bet, not great. Probably would not bet that. But let's take a counterexample. Let's think about, let me take this off. Let's say that I was to make a similar bet, but this time I said, I'm going to bet $100 that I can roll an even number. So if I consider what are my even numbers, on a dice, I would have 2, 4, and 6. So on a dice, I have 3 possible outcomes that would be even. So what's the probability that I roll an even number? Well, I have 3 possible outcomes that are even out of a total of 6. So I would do 3 divided by 6. That would give me 0.5, which means I have a 50% chance of rolling an even number. So considering our original bet of 16%, I had a 16% chance. This bet is a lot better of a choice, I guess you could say, especially when, thinking of like gambling. This is a better bet than the 16 or 17% bet. Or even if I said, what are the odds that I don't roll a 6? Well, if I said, what are the odds I don't roll a 6? My chances of not rolling a 6, so not a 6, well, I'd have 1, 2, 3, 4, and 5. That gives me 5 possible outcomes in which I do not roll a 6. So, considering that, now my odds are a 0.83, which means I have an 83% chance of winning that bet. So you can see the odds now are much, much more in my favor. Okay? So probability is always saying, take the circumstance that you want, not a 6, maybe an even number, however many possible outcomes there are for that event, you're going to divide it by the total possible events. Okay? So hold on to that. We'll come back to that a little bit more when we get into the Venn diagrams and the ands and the or. One last thing before diving into specific examples of probability is I want you to consider theoretical versus experimental. This was something that was talked about in the Khan Academy. So I just want to be a little bit more specific on their details of what makes something theoretical and experimental. So the first thing that I want to, okay, let's pretend like this is a coin, okay? So on one side, I have my heads, and I'm actually going to write on here, heads, okay? So on one side, I have heads, and we're going to call the black side tails, okay? So I have heads and tails. If I were to say, theoretically, what are the odds that I would flip a heads? Okay, well, I'd look at this and I'd say there's only 2 possible outcomes. So however many possible outcomes there are, that's going to be on the bottom. So I have 2 possible outcomes. It's either going to be heads or tails. The outcome that I want is going to go on the top. So I want heads. Well, there's only 1 outcome that would give me heads. So 1. So theoretically, 50%, again, that would be a decimal, turn it into a percentage. If I were to flip this coin multiple times, and I just kind of kept flipping it, and I kept flipping it, and I kept flipping it, and I kept flipping it, 50% of the time, I should expect to get a heads. Because theoretical means that without actually doing the experiment, without actually flipping this coin hundreds and thousands of times, I expect 50% of the time. There's the key word there that makes this different, is I expect. Theoretical is what you expect to happen. Okay, flipping a coin, I expect that 50% of the time I'll get heads, 50% of the time I'll get tails. Experimental is if I were to say, hey, out of 100 flips, how many times do I get heads? So I'd sit here and I'd flip it 100 times, and I would figure out that maybe out of 100 flips, I have 42 heads out of 100. And you calculate that and you say, well, wait a second, that's only 42%. Usually your experimental and theoretical probabilities will not be the same, okay? Actually, the bigger your sample size is, the closer your numbers will get. So I only flipped a coin 100 times, and that's what gave me the 42%. Or actually, your calculators, graphing calculators, have a coin flipping simulation on there, and you could do this exact simulation on there to find out, you know, if I sat there and flipped a coin 100 times, what would be my experimental probability. Again, you're still doing your total number of outcomes that gave you what you wanted. I wanted heads. I had 42 flips that were heads. But I had a total of 100 trials, okay? So the bottom number is your total number of outcomes. Regardless of them being heads or tails, how many outcomes will I have? Well, I flipped a coin 100 times, I'll have 100 outcomes. I just don't know if they're heads or tails. So theoretical is more of your expectations, saying, well, I only have two possible outcomes. It's either going to be heads or tails, so I have a 50% chance of getting heads and a 50% chance of getting tails. Experimental is you actually conducting the experiment, okay? Most of the work that you'll do, especially on paper, is going to be in this theoretical category. They're going to give you numbers or they're going to give you expectations, and you're just going to base it off of the data that you have. Saying, if I had a coin, I have two sides, one side, two sides, two possible outcomes. I want a heads. Well, that's only one of my possible outcomes. So a lot of times theoretical is just not actually doing the experiment, but saying, this is what I expect. And you should probably see that a lot in science class as well. That a lot of times you'll make like a prediction and say, well, I predict that, you know, it's going to be heads 50% of the time. But the reality of it is sometimes a little bit off. And again, the more you do it, the closer you're going to get to that expectation, but it might never be perfect. You might flip a coin 1,000,000 times and it's still not going to be 50%. But it could potentially be getting closer to 50%. Okay, so again, we're going to stick in the world of theoretical, but I wanted you to be aware of that experimental as well. Okay, so I want to go back to this idea of talking a little bit about probability. Give me a second. Okay, so we were talking about the dice earlier, okay? And we said that, you know, we talked a little bit about, you know, what if I wanted evens, what if I wanted a specific number, that type of deal. The thing that I want you to kind of take away when it comes to probability, not only is it always a percentage, but it's always kind of written like this. You have, we'll call it a specific event. We'll call it a specific event. You have a specific event on the top and all possible events on the bottom. Okay, that's how probability always works. Now this is going to give you a decimal, and I just want to remind you of that because once you have a decimal, you'll want to convert it to a percentage. So just kind of keep that in mind. But that's basically what a probability looks like. So how does this relate to this idea of Venn diagrams? So we'll come back to that in a second. Let me go to a Venn diagram for a moment. So Venn diagrams, if you're familiar with them at all, basically are two giant circles with an overlap, right? So if I go ahead and I draw a Venn diagram, put that on there a little bit more. Okay, so I'm going to go ahead and draw a Venn diagram. That was not a good Venn diagram. Not a fan of it. Not a fan at all. Okay. Alright, better. So there's my Venn diagram. In a Venn diagram, you should probably be familiar with this idea, that on one side you have basically one event. Let's do sports. So on this side we're going to have our swimmers. Okay. And then this second circle represents different sports. Let's say soccer players. So in one circle I have my swimmers, and on one circle I have my soccer players. But then you notice that in these circles, there is actually an overlap. A part where both circles cover the same area. Okay? That overlap represents the people that are both swimmers and soccer players. So, let's say that I have a total of 20 swimmers. Okay? So, I'm just going to write that down. Maybe I'll write it up here. So, I have 20 swimmers. And let's say that on soccer players, I have 16 soccer players. Okay? And that's just the number of swimmers I have and the number of soccer players I have. If I have four people that are both swimmers and soccer players, I'm going to put a 4 inside of here. There are 4 people that are both a swimmer and a soccer player. So if I had a total of 20 swimmers, period, regardless, let's disregard soccer for a second. If I had a total of 20 swimmers, 4 of them are right here. That means that 16 of them are on the outside. 16 people are just swimmers. If I do soccer players, again, disregard the swimming for a second. Cover up the swimming. I have 4 soccer players right here, because that's technically part of the circle. 4 soccer players here, which means I have 12 that just play soccer. Now, why is that so important to understand? Because, oh, and actually there's one added detail that we need to consider. How many people overall were surveyed? Be careful here, because it's very tempting to say, oh, 20 swimmers, 16 soccer players, I have 36 people. But you have to keep in mind that 4 people were in both the swimming and the soccer category. So actually, if I go through and I do my 16 plus 4 plus 12, that gives me a total of 32 people that were surveyed. So you might ask yourself, well, what happened to the 36? It's because 4 people counted on the swimmer side and the soccer side. They were kind of counted in both of those. So with the 16, they were counted here. With the 20, they were counted here as well. So they're almost like double counted. So you have to be very careful with considering what's your total amount. How many people are we talking about here? Because it's not 20 plus 16. These two events are not completely separated. They kind of overlap in some way, shape, or form. Which actually brings me to a side note for a second. And I know this is going a little bit out of order, but I think it works right here. Is that idea, and I'm just going to write this word down here so you're familiar with it. Mutually exclusive events. Mutually exclusive means that these two events are completely unrelated. There is no overlap. They don't, affect one another. But these two events are actually not mutually exclusive because there is a point where they overlap. These two events are affected by the other. So if I were to say that all these swimmers quit, that might affect, if every single swimmer quit, then this section here would change. Okay, so mutually exclusive events are two events completely unrelated. Like, let's say the event of picking a heart, if I had a deck of cards, picking hearts, and then also rolling a 6. Those two events are completely separated, okay? Picking the hearts is not going to affect rolling a 6 on a dice, okay? Those events are completely separate. But anytime that there's an overlap in any way, shape, or form, they're not mutually exclusive. Sometimes you'll see, and again, I know I'm sidetracking here a little bit, sometimes you're going to see where they do like, let's talk about grades, right? And if I come down here for a second, there we go. If I come down here for a second and I think about the number of juniors, let's say that's 400 people, okay? And then I say, what's the number of people that are swimmers? And maybe I have 56 swimmers. The thing is, the juniors, some of those juniors might be swimmers, okay? So those two events are not mutually exclusive. But if I said, how many juniors do I have? And how many seniors do I have? Let's say 380, okay? These two events, juniors and seniors, are mutually exclusive. You can't be a junior and a senior. It's just not possible. So mutually exclusive events are usually two things that just are not possible having an overlap, okay? But if there is that possibility of an overlap, then they're not mutually exclusive, okay? So always kind of ask yourself, could there be an overlap? You know, if I'm talking about I think the video on Khan Academy talks about chocolate. Could there be overlap? Could I have something that is both dark chocolate and white chocolate? You know, that's kind of the questions you should be asking yourself. Okay? Oops, upside down. All right. So back to talking about Venn diagrams and probability. And this will bring us kind of back to our last topic of the day, and that's the idea of ands and ors. So when you are given a Venn diagram, you can actually use the Venn diagram to find the probability of a specific event. So what we have in this Venn diagram is really just the overall, you know, outcomes, okay? I could have, 16 people that are just swimmers. I could have 12 people that are just soccer players. And then I have 4 people that are both a swimmer and a soccer player. So this brings in this idea of ands versus or. So when you're doing a probability problem, a lot of times they're going to ask you, what's the probability of this happening? Or what's the probability of that happening? And again, I refer you back to what we had on the other side. When you're talking about probability, you have the specific event that you asked for on the top. How many outcomes do you have there? Over the total possible outcomes. So let's come back to the swimmers and the soccer players for a second. If I asked you, and you can write this down on a piece of paper if you want. If I asked you, what is the probability of selecting a swimmer or a soccer player? What is the probability of selecting a swimmer or a soccer player? That means that I reach into this, hypothetical bag of 32 people, and I am going to pick a swimmer or a soccer player. What are the odds? Well, let's consider all of our swimmers for a second. How many swimmers do I have? I have 20 swimmers. Excuse me. Now let's consider how many soccer players I have. I have 16 soccer players. So anytime you see the word or, what you're going to be doing is basically bringing those two probabilities together. Okay? So keep those numbers in mind, 20 and 16. 20 and 16. So when you're doing an or problem, this is what it's going to look like. You're going to take the probability of the first event happening, so that was 20 possible people that were swimmers. And again, since we're talking about probability, what's the total number of outcomes? That's the total number of students. So we had 32 students that were either swimmers or soccer players. So 20 of them were swimmers. And in the case of or situations, we add the two events together. So I'm going to say, the 20 over 32 going to figure out what that probability is. I'm going to add the probability of picking a soccer player, which was 16, and I would find the probability of that. But here's where the issue comes in. If you calculate that and you say, my 20 plus the 16, that gives me 36 out of 32, and you calculate that percentage, you'll notice that you get approximately 113%. Now, when you do probability, you're never going to get more than 100%, okay? You either have the full amount, 100%, or you have part of the amount. But here, we got 113. Why is that? Why did we get above 100%? That's not possible. I can't have more than 100% of students be soccer and swimmers. So, what went wrong here? What did I do wrong? Here's where OR gets a little tricky. And I want you to think for a second. You had 20 swimmers, 16 soccer players. Where did we go wrong? Where did we go wrong? 20 swimmers and 16 soccer players. Look at this. 20 swimmers and 16 soccer players. All we're really doing is finding the probability of one and adding it to the probability of the other. So where did I go wrong? The problem is the overlap. These 4 students were counted twice. So if I come back to this side and I consider here's the probability of swimmers, here's the probability of soccer players, where we went wrong is we never considered the overlap. So with the overlap, we're going to go back and subtract those 4 people that were in both sections. Now, I want you to understand that we're not completely removing those 4 kids, okay? We're just removing the fact that they were counted twice. Those 4 kids are over here, and those 4 kids are there. So by removing just once, one group of 4, they're still counted, it's just they're not counted in both, okay? So then I go through and I figure out that the probability of selecting a soccer player or a swimmer ends up being 100%. Which makes sense because the soccer and swimmers made up our entire Venn diagram. Everyone on this Venn diagram either swims or plays soccer. So that's why we got 100%. The ands, and the last thing that I'm going to talk about today, the ands, how does that make a difference? The and, when I put and in there, that means the event that I'm considering. What is the event that I want to happen? What is that specific event that I want to happen? Now what I want are the people that are both a swimmer and a soccer player. So if you go to your Venn diagram and you look at all these kids, you have 16 swimmers, 4 in this middle section, and 12 soccer players. We want to know how many people are both a swimmer and a soccer player. Not either or, but they have to be both. So how many students are both swimmers and soccer players? Ask yourself that. How many people are both a swimmer and a soccer player? Not either or, has to be both. So looking at this Venn diagram, where are my students that are both a swimmer and a soccer player? Well, this section, right? This is the section where we have both swimmers and soccer players. So the probability, and that's what the P stands for, probability, the probability of drawing somebody that's a swimmer and a soccer player would look like this. We have, what's my specific event? Well, swimmers and soccer players. That's a total of 4 people out of my total amount of people, everyone in the event. Well, that's a total of 32 people. Okay, so if you had all these people standing in a gym room or something like that, 4 people do swimming and soccer, but there's a total of 32 people standing in the room. Okay, so this is just your specific event. The bottom number is everyone, your total amount. So I would go through and say 4 divided by 32. I get myself a 0.125. I times that by 100 to give me my percentage, and that gives me 12.5%. So again, thinking back to if you were a gambling person, what is the probability of picking someone that is both a swimmer and a soccer player? Do I want to put money on, hey, like, look at all these kids, I'm going to bet $10 that I will get somebody that is both a swimmer and a soccer player? Well, you only have a 12.5% chance of getting somebody that's both a swimmer and a soccer player, so the odds are really just not in your favor. That would not be a smart bet to make, okay? So that kind of summarizes everything we need to get through today. We covered a lot of stuff, so again, consider our agenda here. We talked about permutations versus combinations. Again, permutation, order matters. Combination, order does not matter. The fundamental counting principle is for permutations. Okay, and maybe we'll expand upon that a little bit next week, okay? So we talked about the difference there, saying that, hey, our class is primarily going to be focusing on permutations. Then we got into the idea of probability. We did talk a little bit about experimental versus theoretical. And again, very similar to up here, I told you that we're pretty much going to be focusing right now on theoretical, okay? All these numbers and stuff like that, theoretically, we expect this. But it's not, we haven't actually gone out into a gym and looked at 32 people, okay? It's just all theoretically speaking on paper and pencil. But if I were to go out and actually do it, experimental would be that going out and actually doing it. Then we looked at reading a Venn diagram. Remember that kind of overlap? That's the big difference between ands and ors. And means that I want both things to happen. If I said, what's the probability of flipping a heads and a tails? Well, if I looked at this coin right here, could I flip, if I flip this once, just flip the coin once, could I flip both a heads and tails at the same time? No. That circumstance is not possible. I can't flip a heads and a tails at the exact same time. But what's the probability of one or the other? That's a different situation. That's where you take the probability of one and you add it to the other. Okay? Probability of one and add it to the other. And then we touched a little bit on this idea of mutually exclusive. We will be expanding upon that later. We only briefly looked at the definition of them and basically saying that two events are completely unrelated. There is no overlap between the events. So if you think of flipping a heads and a tails, you can't flip, if I made a Venn diagram of how many heads I flipped and how many tails I flipped, there would be no overlap. This would be my heads over here, this would be my tails. But there's no both. It's not possible to have both. But if I had my list of juniors and my list of swimmers, there could potentially be some overlap there. Okay? So be practicing, think of some ideas of that mutually exclusive, because that's going to be a big determining factor, especially as we dive more into this and or idea. Okay? So for homework, if you have not done Khan Academy, which is all in the material we just covered, you need to go and do your Khan Academy assignment, okay? It is now an assignment. I will be checking that. Please get it done, okay? Most of it is watching videos covering what we just talked about, if not in more detail and giving more examples. And then you also have some practice work, okay?